how's it going, everybody? I am recording our final video of the semester here on Monday, May 3rd, and today we're going to talk about section 6.3, second order Laplace transforms. This is going to build very directly off of what we did in section 6.1. In fact, I would go so far as to say we're basically not even going to get any new concepts today. We're just going to expand the toolkit that we started building in section 6.1. So what I think we should start with is a quick summary of 6.1, everything that we did in the last video, and then we'll kind of ask ourselves which direction would we like to sort of grow in terms of our ability to use this concept, right? So in section 6.1, we started by, we explored a little bit, but we defined our Laplace transform of a function y to be the integral from 0 to infinity of y of t times e to the negative st bt right here, right? So this is in a sense making a comparison between this function and the exponential function right here. And we have performed this operation to find a few general Laplace transforms, right? So the first one that we found was the exponential function. Laplace transform of e to the at is 1 over s minus a. We saw that a special case of this is when you let a be equal to 0. This just becomes e to the 0, which is 1. And therefore we should be getting 1 over s minus 0, which is just 1 over s. So recognize that this one right here is really just a special case of this one here. The other one that's super important because we want to use Laplace transform to solve differential equations is that the Laplace transform of a derivative is going to be negative the function evaluated at 0 plus s times the Laplace transform of the function. The really, really important thing that's happening here is that the Laplace transform is converting a derivative of a function into the Laplace transform of a derivative is equal to just the Laplace transform of the function itself, give or take some addition, subtraction, constant multiples out there, right? That's really important for us. We identified that because Laplace transforms are integral transforms, they get really nice integral properties, such as the fact that constants can get pulled out front. You can split them up over addition, subtraction. That's what we call being a linear operator. We also get the fact that inverse Laplace transforms are going to be unique, and that therefore guarantees that they are also linear operators. And this is just our mathematical notation of expressing what it means to be a linear operator. You can split it over addition, subtraction. Constant multiples don't affect the process that's actually being applied, so we can sort of pull them out front of those Laplace transforms. We very rarely directly use this integral when performing a Laplace transform, but it really matters to recognize that that's what's happening underneath the hood, because that's what should make you feel comfortable with things like pulling the a from the inside of the Laplace transform to the outside, just like you would with any constant multiple with an integral, right? We then used Laplace transforms to solve differential equations. Our three-step process was saying, listen, a lot of times it's really hard to go from the derivative of y to y. We can't do it directly with calculus. Instead, let's take the Laplace transform of the derivative of y so that we're now in a transformed land. Our function of y is now the Laplace transform of the function y. Our parameterization variable over here was t. Our new parameterization variable is s. Once we're in Laplace land, it's pretty simple for us to just do algebra to solve for the Laplace transform of y. We then only need to undo the Laplace transform of y to have finally solved for y. So it seems like it's a longer path here, but all three of the steps in general are often, on average, easier than just directly trying to do the calculus to solve for y, given a differential equation. So the important thing to recognize here is that steps 1 and 3 recognize us to be able to apply a Laplace transform to an arbitrary function or an inverse Laplace transform to recognize the form and to sort of pull back, right? So what that means is that we really want to expand the number of functions for which we know the Laplace transform. The other thing that we recognize is that in the previous video, we only saw Laplace transforms of first derivatives of functions, like this guy right here. Obviously, most of our interesting differential equations this semester have been all of our harmonic oscillators, second-order differential equations, and therefore it seems meaningful to us to be able to find Laplace transforms of second derivatives of a function as well. So today doesn't really, and I shouldn't say it doesn't at all, but we don't really introduce any major new concept. We just want to take this concept a lot further. We started building a tool bag. We want to fill that tool bag with a bunch more tools today. So let's go ahead and do that here. So section 6.3, second order Laplace transform. So what we want to do today is I don't just want to say, let's build more tools. Let's give ourselves at least a little bit of direction here. So the direction that we're going to go in is let's build the tools that we would need to use Laplace transforms to solve forced harmonic oscillators. We know that harmonic oscillators are differential equations that have this type of expression on the left. If there is a forcing function, meaning a force is being applied to the system over time, then we experience the forcing function there on the right. So the thing that we should see right away is that if our goal is to expand our toolkit to be able to solve forced harmonic oscillators, the two big things that we need are, we need the Laplace transform for the second derivative of a function, and we also need to know the Laplace transforms for all of the most common forcing functions that we might end up experiencing in our forced harmonic oscillators. In general, and as the book proposes, our most common forcing functions are experiencing periodic forces, experiencing exponential forces, and you should notice we already know the Laplace transform of this guy, experiencing forces that may be periodic, but with the amount of force growing or decaying over time. So remember that, especially when we have like a negative in the A slot right there, this will be a trig function that is following sort of an exponential curve as it decays to zero. So the amplitude is getting smaller and smaller over time. That's very, very representative of our mass on a spring with friction, where we pull the mass, let go, and we know that the mass is going to wobble back and forth, but eventually come to rest. That's where we're getting those e to the at sine of t's right there. And finally, applying constant forces is also very typical, but remember we also already know the Laplace transform of the number 1, and any constant is a constant multiple of 1. So we've already got that one handled as well. So where we're at is this. We've got that one already, and we've got that one already. We want the Laplace transform of the second derivative, we want sine and cosine, and we want our exponentials with sine and cosine. So that means there's 5 total Laplace transforms that we would like to build for ourselves today. So let's get started. Let's build all 5 of those, and then let's do some applications with them here. So first, let's find the Laplace transform of a second derivative of a function. The reason this one's a pretty easy one to do is because we should always think of second derivatives as just being first derivatives applied to first derivatives, right? I'm thinking of this as in a layered sense right here. So in my mind, this is like the function y is actually x prime. So we're really looking at the Laplace transform of y prime. Well, I know the Laplace transform of y prime. We've already stated it. It's sitting right there. It should be negative the function evaluated at 0. But remember that y is actually x prime in our case. So we'll get negative x prime of 0 plus s times the Laplace transform of the function y. But for us, y was x prime. So we're going to want to do a second layer right there. So let me write this stuff out. So it looks like this should just be s times the Laplace transform of the function we're taking the derivative of minus the function we're taking the derivative of evaluated at 0. Well, there we go. That's only step 1 though, because now I still have the Laplace transform of a derivative. So I could just do the exact same steps again. Why did I just write a 2 right there? I would now like to do s times the function for the s times the output that we get from the Laplace transform of a derivative, which we know to be s times the Laplace transform of the function that we're taking the derivative of minus the function we're taking a derivative of evaluated at 0. And this is what's leading us to our Laplace transform of the second derivative should be equal to s squared times the Laplace transform of the function minus s times the function evaluated at 0 minus the derivative of the function evaluated at 0. So there we go. Not too bad. We just did 2 layers of the first derivative rule to build our second derivative rule right there. So there we go. Of the 5 that we want to build for today, we already knocked one out right here. We're good to go. So now let's look at the list of common forcing functions, right? We already know the constant and the e to the at, so we still need to figure out sine and cosine, and we still need to figure out sine and cosine with the exponential. So those are our 4 remaining. So let's go ahead and find our Laplace transform of sine of omega t. It seems like what we need to do this would be our Laplace transform function right here. This is exactly what it should be equal to. However, what I'm remembering from Calc 2, what all of you that took Calc 2 with me should be remembering, is that this integral right here takes some work. It takes 2 rounds of integration by parts, our dump truck integration, where we then resolve for we never actually evaluate the integral itself. We just solve for a second version of the integral, move it over to the other side, and say, oh, here's what it's equal to. I don't want to do 2 rounds of integration by parts, especially with evaluating them at 0 to infinity. So what we're going to do is we're going to do a much smarter way of building what our Laplace transform will be of sine of omega t. And by the way, just real quick, up here I just said them as sine of t and cosine of t, and here again sine t, cosine t. But in general, we always want to be including like our constant multiples in our consideration right here. So we're really interested in the more general trig function sine of omega t right there. So instead, here's what we're going to do. Let's build an initial value problem that we already know the solution to. In particular, we want the solution to be y equals sine of omega t at the end. So that when we do our Laplace steps at the end, we're going to get down to a value of L of y and we're just going to shrug our shoulders, except for the fact that we actually know what L of y is, and therefore we'll have derived the formula, or excuse me, we'll know what y is, and therefore we'll have derived the formula for the Laplace transform of sine of omega t. It'll just be whatever the other parts are going to be. I feel like me explaining this paragraph is a little bit confusing, so let's watch it happen in action here. So my question to you, and I want to just scroll away from the stuff on the bottom right now, is this. When did we ever set up a differential equation and get our solution to be something like just sine of t? And the first thing I would think to myself, because I'm trying to think as simple as possible, is was there ever a time this semester when we set up a first order differential equation and got a solution of sine of omega t or something like that, right? Or cosine of omega t? And the answer is no. And the reason why not is because if we ever have a first derivative of a function and a non-derivative of a function, if we try and let the function be sine, then you know that the derivative of sine is going to be cosine. And now we've got cosines and sines, and they can't cancel away with one another. Instead, if we have the second derivative of sine, we know that the second derivative of sine is just going to be negative sine, give or take a constant multiple, and negative sine cancels out very nicely with some positive sine. However, if we choose a second order differential equation that does have a first derivative in it, then it's going to have some cosines, and that's again a problem for us. So what I'm thinking here is this. Sine plays really nicely with the second derivative of sine to all go to zero because we get sine and negative sine and they cancel to zero. So it seems to me like I know I need a second order differential equation, not a first, because I don't want sines and cosines failing to cancel. The other thing I need is I need no first derivative in there because I don't want cosines to get introduced. I just want sines and negative sines to cancel to zero so that we can easily solve the differential equation. Remember that the first derivative is what we referred to as our damping term because our first derivative is what affects things like friction, right? And friction is opposed by velocity. That's our damping term there. So what it seems like we're interested in doing is building an undamped harmonic oscillator. Right? What I know is I would like to have a y double prime term, but you could also tell that if we take two derivatives of y, what we're going to get back is negative omega squared sine of omega t, because two of these omegas are going to get popped out from the two derivatives. Sine will go sine to cosine to negative sine when we take the two derivatives. That's where the negative is coming from. So what I think I want to build for my second order differential equation is something where that's all going to perfectly cancel out together here, right? So notice here, and we're going to go ahead and check this. Here is my undamped, it's not damped because there's no y prime term, harmonic oscillator. And we can also tell, based on our Laplace transform definitions, it's really important that we're able to identify the derivatives. We need to know their initial conditions, right? We always are going to need to be able to evaluate these functions at zero, the function and the first derivative at zero. So I've got to identify my initial conditions. So the first thing we should do is let's just go ahead and check that we're not being crazy right here. Let's go ahead and check that y equals sine of omega t is in fact a solution to this equation and does satisfy these initial conditions. So the first thing I'm going to check is that the second derivative here, if I take two derivatives of sine of omega t, two derivatives of sine gives us back negative sine. Two derivatives with the omega on the inside is going to pop out an omega squared. So negative omega squared sine of omega t plus omega squared, this is just sitting out in front of the y, times y, and we're saying that y is sine of omega t. Yeah, well, it looks like these perfectly cancel out and give us 0 equals 0, so I'm good with this component. The next thing that we need to see is that if we plug in 0 into sine of omega t, then this is just saying sine of 0 equals 0. That's all good. The other thing I know is that the derivative of this function right here is omega cosine of omega t. And then when we plug in 0 for this guy, we're getting omega times cosine of 0. Cosine of 0 is 1, so we just get omega. That is equal to omega, and so we're getting another check mark right there. So it seems like we've confirmed that y equals sine of omega t is the solution to this differential equation with these initial conditions right here. So what we're now going to go do is we're now going to go, in a sense, pretend we didn't know that. We're going to attempt to solve this differential equation using Laplace transforms, but we won't actually be able to do the last step of undoing the Laplace transform, but that's okay. All it's going to do is show us what the Laplace transform of sine of omega t must be. So check this out right here. This is a pretty cool technique. So let's go ahead and take the Laplace transform on both sides. Oops, the Laplace transform of 0. But remember, you should be comfortable saying that the Laplace transform of 0 is 0 because the Laplace transform of a function is essentially, that's 0. 0 times anything is 0. So this is going to be like taking the integral of 0 from 0 to infinity. That's going to give us 0 right there. So I think I can write this next line as L of y double prime plus omega squared Laplace transform of y, because it's a linear operator, so I can split it over addition, subtraction. I can pull out constant multiples. Laplace transform of 0 is just going to be 0. And now I can use the formula that we just built to get our second derivative Laplace transform here. So we just determined it was going to be s squared times the Laplace transform of the function minus s times the function evaluated at 0. And notice the function evaluated at 0 is going to be 0. We've got that stated right there. Minus the derivative of the function evaluated at 0, which we know is going to be omega right there. So we've got that this is going to be s squared Laplace of y minus s times y of 0 minus y prime of 0 plus omega squared Laplace of y should be equal to 0. And remember, we already know what y is. That's our trick with this one right here. I hate calling things tricks in math, but all of our Laplace transform stuff is a little bit like a trick coming up with the new Laplace transforms. Using them is fine. Deriving their formulas, all of them have these little sneaky tricks to get to them right here. And I hate thinking of math things as tricks. These are kind of like tricks right here. Y of 0 we know is 0. Y prime of 0 we know is omega. So I think it's going to be reasonable for me to rewrite this as this. So now what I'm seeing is this. L of y is what we're looking to solve for, right? So I'm seeing what's up with the Laplace transform of y. How much of that do we have? What are the coefficients of that in our equation so far? Well, I've got s squared of it here, and I've got omega squared of it here. So it looks like I've got s squared plus omega squared is how much Laplace of y I have. This term went to 0. S of y of 0 went to 0 because y of 0 is 0. Y prime of 0 we were given as omega, or we confirmed that it should be omega. So I'm going to go ahead and just add this term to the, or whatever. I'm not going to do too many algebra steps all at once. Well, I'm doing too many at once. You guys can do algebra. I don't care. I'm going to just go ahead just to finish this problem now. Add omega to the other side, divide by s squared plus w squared, and we're finding that Laplace of y must be omega over s squared plus omega squared. And the cool thing is that we already know what y is. We have already proven that in this scenario, in this initial value problem, y is sine of omega t. That is the solution to that initial value problem. And so that's going to tell me that the Laplace transform of sine of omega t must be omega over s squared plus omega squared. And that is a really cool way for us to come up with a new formula for a Laplace transform right there. We built the differential equation that had the desired function as a solution, and then we did step 1 and step 2 of our solve the differential equation using Laplace transforms. We didn't even care to do step 3 because the whole goal was for us to determine, in our case here, not what is y equal to. We already knew that. We wanted to know what's the Laplace transform of y equal to, and that's where you always end at the end of step 2 when solving a differential equation using Laplace transforms. So very cool, sneaky way to go about this. Last thing I want to say about this before we go on to our next one right here is this. Right now, this just looks to you like there's two different letters involved in this, omega and s, but you need to remember, s is really our parameterization variable of time in Laplace land. So s is really like t. On the other hand, omega is really just a constant. It's going to be a number like 6. So this has the only variable in this is the s squared that's on the bottom. These omegas are both constants right here. That's an important kind of distinction to make. That's not like I don't visually see that. I have to like remind myself of that when I see this. So now let's do some more tricks. Now that we know the Laplace transform of sine of omega t, it should be the case that the Laplace transform of cosine of omega t should be very much nearby, because sine and cosine are very nearby to each other in a calculus sense. And especially since the Laplace transform is a calculus operation, it seems like we should be able to use the calculus relationship between sine and cosine to help us go from the Laplace transform of sine to the Laplace transform of cosine. So let's go ahead and do that here. So what we're going to do is I'm just going to identify that the derivative of sine of omega t is omega cosine omega t. The omega gets popped out by the chain rule right there. Well, our whole goal is just to find the Laplace transform of cosine of omega t, which is sitting right there. And I know about the Laplace transform of this stuff. So let's just hit both sides of this simple equation with the Laplace transform. Now, I know that that omega certainly doesn't impact what we're looking at right here, so I pulled it out front right away. And over here, this should look, you should right now be like, ugh. But remember, we have a rule for this. We just normally use this rule generically, and now we're using it for a particular function. We have the Laplace transform for the derivative of a function sitting right here. It says you should evaluate the function at 0. So we're going to evaluate sine at 0 and get 0 for this negative term right here. Plus, it should be s times the Laplace transform just of the function, sine of omega t. We just found that. So we can use this rule right here, right? So this should be the negative of sine of 0t, or sine of 0, sorry. This should be negative sine of 0 plus s times the Laplace transform of the function that we're taking the derivative of, which in our general version is just y. Here, our function was sine of omega t. This should be equal to omega times the Laplace transform of cosine of omega t. We know that sine of 0 is 0, so we're done with that term. We know that the Laplace transform of sine of omega t is omega over s squared plus omega squared. And it looks like we're basically done. Just a smidge of algebra to go. All I'm going to do is divide both sides by omega. They cancel. And it looks like what we're getting is s over s squared plus omega squared is the Laplace transform of cosine of omega t. So once again, I hate it when people refer to anything in math as a trick. But man, these feel like tricks. And they're not. It's just how math works. But man, it feels tricky. So again, I want to highlight to you an important thing right here. Remember that in this case, omega is just a constant. S is the variable that is parameterizing our equations out here, right? It's doing the job of t, except it's doing the job of t in Laplace land. S and t are sort of like equivalents for one another. T is in our regular space. S is in our transformed space. It's our parameterization variable. So this equation over here for sine of omega t only has one variable in it, s, and the omega terms are constants. This has both a variable squared on the bottom and a variable up in the numerator up here. So this one's a little bit different right here. All right. So the good news is we've already done our Laplace of our second derivative. We've done our Laplace of sine and cosine. All we need is the two for e to the at sine omega t and cosine omega t here. So let's do them. You should initially expect that finding these Laplace transforms is going to be hard because these functions are like composite functions. We're dealing with trig and exponential parts together. However, you should notice that these are going to play pretty dang nicely with our integral definition of the Laplace transform, because the integral definition of the Laplace transform also includes like an e to the power of something t term in it, like we're going to have in this function right here. So it's going to play pretty nicely with that. So what we're going to do is we're going to just use some generic notation to recognize what's happening here. So what we're going to say is this. For some general function, lowercase f of t, it's untransformed, so it's in terms of t, and it's our original function, so we're calling it lowercase f. Let's use the notation that when you take the Laplace transform of this lowercase f function of t, that you're getting back capital F of s. S is our parameterization variable out in Laplace land out there once we've applied the Laplace function, right? So using that notation, then what we're going to get is that when we try to apply the Laplace transform to e to the at of f of t, and remember, we're kind of thinking f of t is like sine of omega t here, but I'm not even trying to be that specific. I'm thinking even more general than that, right? So I'm thinking of just like this as what we normally call just like y, and we can see that we are just taking the integral from 0 to infinity of y times e to the negative st. That is our definition of the Laplace transform. You should notice that what we're getting here is the integral from 0 to infinity of f of t times e to the a minus st dt. All right. Now, you should generally recall, on the other hand, our simpler version of this being the integral from 0 to infinity of just f of t e to the negative, very important here, at, not st, dt. This is what we just call f of s, right? Now, up here then, this is, oh my gosh, no, I was right. Wait. So now I'm confusing myself. Sorry. Our integral transform definition totally does have the s. I know to be careful with it, and that's what made me get overcautious and write it in the wrong place right there. So here's the thing you need to see. In our basic, this is just literally the definition of the integral transform right here in blue, right? The Laplace transform. Notice that negative s here corresponds to positive s here. So it seems like, what are we going to get from this guy right here? Well, it seems like we're just taking the negative of the coefficient on t for capital F of whatever. Well, the negative of the coefficient on t is s minus a, so this should be f of s minus a. So the important thing to see here is that even though we haven't very specifically gotten the Laplace transform for this function right here, what we're recognizing is that it should only differ from the Laplace transform of just sine of omega t by a horizontal shift. This is like us doing the Laplace transform of sine of omega t and getting out, something that looks like this. I guess that's for cosine. We're recognizing that if we were to then attach on the e to the at term to that as well and do the Laplace transform, it's just going to be a shifted version of whatever we got from just sine or cosine right here. So the Laplace transform of e to the at sine of omega t should just be a shifted version right, where we're swapping out s for s minus a. That's the only shift that we're going to experience. So what you can see here is when we have this Laplace transform of cosine of omega t, when we look for the Laplace transform of e to the at cosine omega t, we're just going to see some s minus a's, where we used to see s in the previous expression for the Laplace transform of cosine omega t sine omega t right there. So rather than just kind of like generally stating them, let's just do a couple examples with them here. One forwards direction, one backwards direction here. Right? So let's evaluate these two expressions, a Laplace transform and an inverse Laplace transform here. So what I want to recognize is that since this expression right here, the Laplace transform of an e to the at cosine omega t, it should just be a shifted version. It should just be a shifted version of the Laplace transform of cosine of 2t. Right? We just saw up above that the e to the at term just applies a shift once we're done. Right? And we know that the Laplace transform of cosine of 2t, well, we just did this up here. What do we get? We got that the Laplace transform for cosine of omega t is s over s squared plus omega squared. We have cosine of 2t, so we're going to get a 2 squared in that spot. So I'm just seeing s over s squared plus 4. So the shift is that we want to replace s with s minus a, which is equal to s plus 3. And so it seems to me like we should be arriving at the conclusion then that the Laplace transform of e to the negative 3t cosine 2t should be almost exactly the Laplace transform of cosine of 2t, just shifted by 3 units. So we got s over s squared plus 4. I just want to shift that by a few units right here. So it should be that we're just going to get s plus 3 over s plus 3 squared plus 4. And we might want to expand that in the denominator down there to write this as what? S squared plus 6s plus 9 plus 4. So that's a plus 13 right there. All right. We've got our Laplace transform of e to the negative 3t cosine of 2t. And again, we're recognizing that when we include the exponential term as an additional factor in the thing that we're trying to transform, it's always only going to shift us by a units, where a is the coefficient on t, because of the fact that there's already an e to the negative st within our definition of the Laplace transform. And so it's just grouping this coefficient in with the coefficient that was already there. That's why this is just a shift for us there, right? So I think that this direction is the slightly easier direction. I think this is a little bit trickier for us to do with the inverse one, but having seen the forwards direction, we're just going to mimic it backwards. So you should notice that we're now in a function over a quadratic, where just like you see here, a function over a quadratic, we're just going to kind of work from bottom to top of the example that we just did over here, right? So first I'm thinking to myself, because I see a quadratic in the denominator, the only Laplace transforms that I know that are associated with quadratics in the denominator are sine and cosine. Very importantly, you should notice that both of these only have an s squared. Neither of them have an s. The only way that we're going to introduce a term that has just an s in it, like we have in our example down there, is if there is a shift associated with this. If it was like an s minus 7 squared, then that would expand and it would give us all three components of a quadratic, right? So I'm thinking to myself, it's typically better when we see this quadratic in the denominator to complete the square and then undo the shift. And that will give us something that looks like our sine or cosine Laplace transform. So let's go ahead and do the completing of the square here. So this should be the Laplace inverse of 1 over, I'm thinking this is s squared plus 2s plus 1 would be the perfect square trinomial. That would condense down to s plus 1 squared. But there's a plus 5 out there instead of a plus 1, so I need a plus 4 to make all my components agree with one another right there, right? So what I'm thinking to myself is, this is what I'm thinking of as my shifted version, because I'm seeing that s plus 1 that's sitting in there. So we've got a shift of s seems to be written as s plus 1, where we really know that this is like s goes to s minus a. And so it seems to me like a equals negative 1. And so we'll have an e to the negative t term in our answer. From the shift. Since we have that component, let's now ignore the shift. Right, so I know that's one component of my answer. I'm now going to, in a sense, ignore that that's an s plus 1 and just call it s and see if I can find the other component of my answer, right? So now I want to know the Laplace inverse of just 1 over s squared plus 4, right? And so I want to now scroll up and say, well, I don't know. It seems to me, I feel like I remember this is one of my trig ones. I don't remember which one. Let's scroll up and see, is this going to be sine or cosine right here is really my question. So we have a constant over s squared plus a constant. It's got to be sine, right? Because cosine has an s up in the numerator and we don't. We need just a constant up in the numerator, right? Unfortunately, our coefficients don't seem to match up. All right, we've got the Laplace transform of, sorry, well, I'm forgetting here, sine of omega t is omega over s squared plus omega squared. Oops. And so what seems to me to be the case is this. It must be that, so we have that 4 equals w squared. And so it seems like omega could be positive or negative 2. I'm just going to keep my positive version for right now, omega equals 2. But you should notice that that means that we need 2 in the numerator as well. Because we need an omega up in the numerator. So here's the way that I'm going to write this for myself. Apparently I need a little bit more room. Is that I'm going to write this now as the Laplace inverse of, I needed a 2 up in the numerator, so I'm also introducing a factor of 1/2 to cancel it away, because I don't want to alter what I've got here. And now this seems to me to be in exactly the format that I want this to be. 2 over s squared plus 2 squared. That's going to be exactly 1/2 of sine of 2t. And so now, because we got the e to the negative t from ignoring the shift, or from handling the shift, recognizing the shift, then we ignored the shift and found the other component, the 1/2 sine of 2t. It looks like our overall answer then is going to be that the Laplace inverse of 1 over s squared plus 2s plus 5 is going to have to be e to the negative t, 1/2 e to the negative t sine of 2t. The e to the negative t came from the shift. The 1/2 sine of 2t came from the quadratic components. So notice you'll regularly have to play little games to make your numerator be what it needs to be by introducing an additional factor up front. In a sense, that's sort of just like doing like what we do with u sub, right? So nothing too crazy there, but sometimes you got to play around with your constants to make everything meet up right there. Very cool. So we've got our couple. So we built all of the Laplace transform inverses that we want to today. However, you should hopefully now also realize that there's still a ton of functions that we haven't covered yet, and that every single one of these Laplace transforms that we've done, they all seem to have some special idea or some trick to figuring them out. I hate saying trick, but they all have them. Fortunately for us, there's plenty of smart people that have come before us to figure these things out. And so all we really need to do is go to the internet and look up a Laplace transform table to see what all the rest of these look like. So we're not going to derive any new Laplace transforms on our own. We're now going to say, listen, we came up with Laplace transform for an exponential, for a constant in the last video, for first derivatives and second derivative, last in this video, sine and cosine, and exponential sine and exponential cosine. We've come up with 8 Laplace transforms on our own. There's still probably 100 of them that we'd care to know out there, and this has taken us like a week of work just to get 8 of them right here. We're not going to get any more. But the good news is that people that deal with Laplace transforms regularly, which is primarily engineers, just basically keep handy a sheet of Laplace transform relationships out there. So let's briefly go to the internet and take a look, and you will see that although this might be a thing that you maybe never heard of before this week, you're going to laugh when you Google it and see if there's infinite resources available in association with this. So over here at Google, I have just Googled Laplace transform table, and what you're going to see is going to come up is just, table of Laplace transforms, table of Laplace transform, list of Laplace transform table, table of Laplace transforms. There's just a crap load of these out here. It seems like every single professor on earth has come up with their own table out here. I gotta say, I actually somewhat don't quite like the... Come on, internet. I feel like the Paul's online math notes, I know it's a thing that most students are used to, but I don't know. I'm not in love with this version of it right here. But anyway, you can see this table includes 37 of the most needed Laplace transforms that we have available, and you should see some ones that you recognize. Laplace transform of a constant is 1 over s. Laplace transform of an exponential e to the at, 1 over s minus a. We've done those. We didn't do t to the n power, but there's our Laplace transform of it. Other powers we didn't get. Here's our sine and cosine. These are exactly the ones that we did today. They just have a's instead of omegas. We didn't do these ones with the t's sitting out front, but you can see their structure is sitting right there. A whole bunch of sums of and differences right there of ones that involve a t on one term but not on the other. Those are a little bit weirder. What else did we get? We did these two just now, 19 and 20, and you should notice these are just these shifted versions right here. This highlights terribly. The shifted versions of the sine and cosine ones from above. So those are all the ones that we've got. The only other ones that we've seen are the first and the second derivative, and it's s times the Laplace transform at s minus the function evaluated at 0, s squared times the Laplace transform of the function at s minus s times the function evaluated at 0 minus the derivative of the function at 0. Those are all the ones that we've already seen out there. So all the ones we've done are completely accurate to the table that we're seeing, plus tons of others. So now if you ever come up against a function you've never seen before, boom, you're just going to dig it right out of a Laplace table right here. Just go and look this thing up. As I said, this honestly isn't my favorite table. I'm looking, where's the one that I feel like I've used a whole bunch before? I feel like this is the one that I feel like I've seen the most often right here. I know this is really small and hard for you guys to see, but the point is, go online and find a PDF that's something that you ever want to look up stuff off of. It's going to be the case that in your homework, you're going to be expected to perform some Laplace transforms of functions that we haven't dealt with in the notes. That's okay. You're just going to look them up in a table and be like, oh, that's the transform right there. The work ends up being in deriving them for the first time, which we've done a lot of on our own, but no sane person ever rederives all these on their own. And we know that the work in solving the differential equations actually just comes from the algebra in between applying the Laplace and the inverse Laplace. So this just has kind of the stuff that we need for ourselves in the table. So I'd encourage you to go to Google. You Google for Laplace transform table. You find the one that's the resource that you like to use. They're all ever so slightly different from one another, but they're all going to have like 30 something on there, and 25 out of the 30 are probably going to overlap with like every single table that you're going to find out there. So it's all out there. So this is one of those things where you are expected to use a table to look these up. Again, nobody just learns all of the Laplace transforms. It's just not that's not a reasonable use of our time. Whether we would cover this topic for a week or for a month, we still wouldn't cover more transforms. We would just do more stuff with the transforms that other people have already figured out for us. So know that you are expected to look these up in a table. That's how mathematicians deal with Laplace transforms. So there's a table, and maybe we need to look some up for the examples today. Maybe we don't. We'll see as we go along here. So now that we've come up with all the Laplace transforms I care to derive with you, let's use these to do some more examples here. So let's go ahead and let's find the particular solution to the forced undamped oscillator x double prime plus 4x equals 3 cosine of t, where both the function and its derivative at 0 start at 0 here. So let's see if we can find the particular solution associated with this guy. The first thing I want you to notice is that because this is an undamped oscillator, we know that undamped oscillators are the things that have no damping force. So when we pull the mass on the spring and let go, it's just going to oscillate back and forth forever. Right? That means it's got only sines and cosines in its general solution here. And so for the homogeneous, I'm just going to say lambda squared plus 4 lambda equals 0. You should notice that that's going to tell us that lambda is going to be plus or minus 2i. And you should notice that that's going to tell us that our homogeneous solution for x is going to be like a k1 sine of 2t plus k2 cosine of 2t right there. Right? So that's just our homogeneous solution. We're interested in using Laplace transforms to find our particular solution. I'm just bringing this up because we're going to see a little bit of overlap between the homogeneous and the particular solution, so I just want to be able to reference that at the end. So let's go ahead and do it. Let's hit this thing with a Laplace transform. X double prime plus 4x is in the Laplace on the left. I'm trying to be respectful of my just do something on both sides here rather than trying to do too many steps at once. But what we know is that, again, I've said this a bunch of times, we get to split up our Laplace transforms over addition and subtraction. We get to pull constant multiples out front. So the good news for us is that we know how to handle the two unknowns here. Remember that our goal is to solve for the Laplace transform of x, so that's the thing we're trying to solve for, so I'm going to just leave that one alone. Our formula for the Laplace transform of x double prime was s squared Laplace of x minus s times x at 0 minus x prime at 0. That was our Laplace of x double prime. Plus 4 times the Laplace of x equals 3 times, and I always forget between the cosine and the sine here, the Laplace of just, oh, sorry, by the way, this is just the Laplace of just cosine of just t, just cosine of 1t right there. So our Laplace transform for cosine was of 1t should just be s over s squared plus 1. All right, so our goal, so we've done step 1. We've applied the Laplace transform to both sides of the differential equation. Step 2, use algebra instead of calculus to now solve for the Laplace transform of x. And so what I'm seeing here is how much Laplace of x do we have? Well, I've got s squared of it here, and I've got 4 of it here. This term is 0 because x of 0 is 0. This term is 0 because x of 0 is 0. So those are just gone. So we have equals, and it looks like this is 3s over s squared plus 1. So it looks like what we're getting for our Laplace transform of x is we are getting 3s over s squared plus 4, s squared plus 1. So what we need now is we need an inverse Laplace transform for this function down here. You should notice that this is a product of two quadratics in the denominator. So I'm going to pop on over to Desmos here, and I'm going to go say, hey, why is this giving me, how do I, oh God, oh, thank you, Pinterest, for our Laplace transform table. No, thank you. Just give me the full screen one, damn it. Where'd that go? So looking over here at Paul's online math notes, what I am just doing now is I'm just hunting down the right-hand side because I want to bring a Laplace transform back to T land. We're currently in terms of S, right? And so all I'm looking for is something that has a product of two S squareds on the bottom. It's half powers, S squared, S squared. S squared plus A squared squared, so I guess it kind of could be like that, but only if they were the exact same thing, and they're not. So those are close, but not quite right. Everything I'm seeing just either has like a s squared plus a squared squared, which is too specific, or just a single s squared on the bottom. Hmm. 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 Didn't see one. So that's a bummer. So what does that tell us that we actually need to be able to do now? Is I could handle this if this was ripped apart into two fractions. Don't you guys really enjoy the fact that all this just boils down to us just doing partial fraction decomposition is now the hard part of this rather than actually calculus being the hard part of this? So let's go ahead and do the partial fraction decomposition. So I need to be able to bust out 3s over s squared plus 4 times s squared plus 1. What I'd like this to look like is a fraction with an s squared plus 4 in the denominator and a fraction with an s squared plus 1 in the denominator, because both of those I could work with as like a sine or a cosine or something like that. Since these are irreducible quadratics, we need to have entire linear terms up top, as plus b and cs plus d. We can't just do a constant necessarily. Maybe that's going to work out, but we need to include all the possible terms that we might need up there. So let's go ahead and do it. So 3s, I'm going to multiply by this entire denominator here. This should be giving us as plus b times s squared plus 1 plus cs plus d times s squared plus 4. I'm going to expand this to get 3s equals, so what do we got? As cubed plus bs squared plus as plus b, and then cs cubed plus ds squared plus 4cs plus 4d. Now I know that I want to group these up not by their a's, b's, c's, and d's, but by how much s they all have within them. So I'm going to write this as 3s equals. How much s cubed do I have? A of it plus c of it. How much s squared do I have? B of it plus d of it. How much s do I have? That's the thing that's actually surviving on the other side over there. A of it plus 4c of it. And how much constant stuff do I have? B plus 4d. All right. So it seems to me from this equation that it should be, there's no cubic stuff on the left, so a plus c equals 0. So I know that a is equal to negative c. It seems like there's no squared stuff on the left. There's no s squared over here. So b plus d is also equal to 0. So b is going to be equal to negative d. I have that a plus 4c is actually going to be equal to 3, because that's how much s stuff we have on the other side. And notice we can actually now solve this equation. I know that a is the same as negative c, so I think I can say negative c plus 4c equals 3. It seems like 3c equals 3, and c equals 1, and so a equals negative 1, so I've got those two right there. It then also seems to me like I've got b plus 4d is equal to 0. So what else can I do over here now? It seems like I have b plus d equals 0 and b plus 4d equals 0. Well, I know a relationship between b and d. So negative d plus 4d equals 0. So 3d equals 0. So it looks like d equals 0. And if d is 0, the negative of d is b. And so I'm going to get b equals 0. So I've got my 4 parameters for partial fraction decomposition right there. It seems like neither of them needed the constant term up here, b and d, both of them did need the first order s term up there. So we did our partial fraction decomposition. That's actually the hard part of this problem right here. And so it seems like I can now write my Laplace transform of x as we got negative s. I'm going to want to, well, whatever. I'm going to just write this. That's fine. Negative s over s squared plus 4, because we had a was negative 1, so that should go with this grouping. We should have that c is positive 1 and d is 0, so we're just going to get plus s over s squared plus 1. And so what are we going to get from this guy when we do... Come on, get out of here. Go to the next page. What's wrong with you? There we go. So now we're good to go to apply our inverse Laplace transform. And I know that we're okay to do that because I recognize both of these as being exactly the format of things that I know that I can pull back from, right? These are what we get out from Laplace transform, so I can now undo that. So I'm now going to apply the inverse Laplace transform to both sides of the equation. I'm going to be formal about the way that I'm writing this here. There's certainly some steps that I could skip that I'm okay with you guys kind of in a sense skipping here, but I just want to write out all the work to make sure we see exactly what's going on. So this should be negative Laplace inverse of s over s squared plus 4 plus the Laplace inverse of s over s squared plus 1. And just from a brief look back at what we've previously found today, s over s squared plus 4, s over s squared plus 4 just means that omega is 2, so we're going to get cosine of 2t. S over s squared plus 1, omega is 1, so we're just going to get cosine of t. So cosine of 2t and cosine of 1t are the two things that we're getting from these inverse Laplaces right here. So this will be x, and this is, notice our particular solution, negative cosine of 2t plus cosine of t. Awesome. So finally, what you should notice is that cosine of 2t was also part of the homogeneous solution, which we stated right here. Cosine of 2t is part of the homogeneous solution. So it would typically be the case, and again, if you go ask Wolfram alpha for the solution to this differential equation, it's just going to tell you k1 sine of 2t plus k2 cosine of 2t, but that k2 cosine of 2t is actually also grabbing this term from the particular solution, so it will also just have plus cosine of t on the end right there. Also in our homogeneous solution, so we get x of t equals our k1 sine of 2t plus k2 cosine of 2t. Remember, k2 cosine of 2t came from the homogeneous, but in a sense, this is just an additional constant multiple of more cosine of 2t, so it's sort of getting absorbed into the k2. So I would just say here plus cosine of t, and that's what you'll see if you go look up this guy in Wolfram alpha. It'll only have the cosine of t, not also the negative cosine of 2t, because it just got grouped up, so it got absorbed by the k2 right there. So this technically was the answer to the question that we were actually asking in this problem, though, right here. So really cool, and once again, you're seeing partial fraction decomposition often arises in these cases right here. And on the one hand, you should groan loudly, and on the other hand, you should say, I guess it's pretty sweet that just doing an algebra problem is the hardest part of the hardest calculus class right here, because Laplace transforms take all the difficulty of a problem and they put it in algebra land instead of being in calculus land, and that is definitely good for us right here. So very, very cool. So we just solved our first second order differential equation by using Laplace transforms right here. Very neat. Let's go ahead and do our last example of the semester right now. I can honestly say that I am devastated because I really like this class. Resonant forcing. So for this example, we want to solve another differential equation. You should see that this differential equation looks a ton like this one did, right? Second derivative is there. First derivative is not. Zeroth derivative is there, and then just a trig function on the right. Second derivative is there, no first derivative, zeroth derivative is there, just a trig function on the right. So what's different about this one? What's the homogeneous solution to this differential equation? Well, I can just real quick do my lambda squared plus 9 lambda equals 0. A quick look here, because that's a plus instead of a minus sign, says that I'm going to get lambda being plus or minus 3i, and that tells me that we're going to get our homogeneous solution for x should just be a k1 sine of 3t plus k2 cosine of 3t. Now here's the really important thing that's happening. This homogeneous solution is what would happen if we just set the system off and just let it go. Right? That's what the homogeneous solution is describing, as if we were just releasing it and nothing else happened. However, what you can see here is we are not doing that. We also have a forcing function of cosine of 3t. And what's special about that is that our forcing function is periodic. Our homogeneous solution is periodic. And they're periodic with the exact same periods. That's something really, really, really special. All right. Very special when our homogeneous solution is periodic and has the same period as the forcing function that's also being applied, right? So this scenario that we're modeling right here naturally oscillates with a period of 2 pi over 3. We are also going to apply a force to this system with a period of 2 pi over 3. So when the homogeneous solution and the forcing function are both periodic with the same period, that's when we experience resonance, right? When an oscillator is resonant, the sinusoidal waves combine constructively to add together, as opposed to combining destructively where they cancel out. So this is like in every Looney Tunes cartoon where there's an opera singer that sings and shatters the wine glass. If the natural resonant frequency of the wine glass is some certain period, and the singer is singing with a frequency that matches that same period, then the wine glass that's vibrating is going to vibrate more and more until it just explodes and shatters. That's resonant forcing right there, when the force that you're applying to the system matches the natural frequency of the system. So they add together over time, giving you bigger and bigger waves until things wobble and fall over. Who cares besides Daffy Duck? Well, it turns out this is how buildings fall over in the wind. If when the wind blows, it makes the building wobble lightly back and forth, which, by the way, I don't know if you guys know this, but if you're ever in a tall building, you can feel, if you're like up on the 80th floor of a building ever and it's windy, you can feel the fact that you're wobbling back and forth a bit. And buildings are built with if they were perfectly rigid, then one strong wind would shatter them. We don't want that to happen. Buildings are meant intentionally to be flexible so they can deal with that. But if you were to blow the wind at the building with the appropriate period that is equivalent to the natural swaying period of the building, then it's going to build in its frequency back and forth until it tips over, right? Another example that some of you guys may be familiar with associated with resonant forcing is a very, very famous example. I'm bringing it up for a reason right now. Let me get to the end of my statement here. Is the Tacoma Narrows Bridge. And I encourage all of you, stop right now and check out a quick YouTube video of the Tacoma Narrows Bridge. This is when they built a bridge in Tacoma over the big bay near like Tacoma and Seattle right there. And then like literally on opening day of the bridge, it was really windy and the bridge just started wobbling back and forth and literally just collapsed into the bay. And so this has been described as such a perfect prototypical example of resonance that a lot of textbooks literally have an entire special topics section on specifically the Tacoma Narrows Bridge. Unfortunately, this is one of those things where our mathematical understanding of what happened back there in whatever it was, the 50s, 60s, or 70s, or whenever it happened, has been upgraded since then. And I am quite certain that it has been the case that we have since determined, engineers have since determined, that the bridge actually didn't collapse due to this resonance building an amplitude and causing it to break down. Is actually something else going on out there. So it actually turns out that that was not an example of resonance right there. But I mean, it's commonly associated with that. And we do have this idea where if something is wobbling and the way in which it's wobbling is growing in amplitude over time, in almost all real world situations, that's going to break the scenario. It's going to break the physical object. If you're an engineer, resonance is something that's kind of scary that you want to stay away from. Growing in amplitude sinusoidal waves is a dicey thing. Right? Because it eventually means you're going to be, having huge amplitudes back and forth in your swing. It's going to break whatever it is that you're trying to build. So basically all we're saying is we want to think about what was going to happen here before we see the solution, and then we're going to see that the solution agrees with what we predicted is going to happen here. So in this case, what we should expect to find is this. I'm expecting to find a particular solution to this differential equation that is periodic, because we are experiencing periodic motion when there's no force being applied, and we are experiencing a periodic force being applied. So I'm expecting the long-term behavior of x to be periodic. But I'm also expecting that because the amplitude of the homogeneous solution, what would happen if it's left alone, matches the period of of the forcing function, what the force we're actually applying, that we're expecting to see the amplitude of the periodic function growing over time until the system breaks, whatever that means in the context of your problem, right? So let's go ahead and solve this differential equation. I did give some more initial conditions to go along with it right here. And again, what we're expecting at the end is to get a solution that meets those two, suggestions right there based on our verbal description of what we think is happening. So let's go ahead and do this thing here. And again, this structure of this equation looks crazy close to the structure of the previous one, but I don't think we're just going to get some nice sines and cosines wobbling back and forth. These maintain their amplitude forever. I'm expecting to get something that grows in amplitude over time. So I'm expecting to get a different structured solution. So let's go ahead and do the dang thing. And this is our disappointingly last problem of the semester here that I will be doing. So Laplace transform x double prime plus 9x. Maybe I should just do typos for 30 minutes here so I can drag this out. I know that you guys just like hearing my voice. Don't forget, you can just go watch these videos on YouTube like every day for the rest of your life if you ever miss these videos here. Don't worry. So nothing too crazy happening here when I apply the Laplace to both sides. I separated the addition, pulled the 9 out. We can go ahead and apply our known equation for the Laplace transform of the second derivative of a function. I always forget my Laplace transform of my cosine versus my sine. I always forget which one it is. Let's look it up in a table this time instead of scrolling up. So cosine of 3t is what we want to transform. So I'm just going to scroll over here until I see cosine on the left. And just cosine is all I want. So cosine of 3t right there, it's rule number 8. And it looks like we're going to get out s over s squared plus 3 squared. So s over s squared plus 9. S over s squared plus 9. I know that our initial conditions for both of these were 0, so both those terms are gone. So it seems like I've got the Laplace of x. How much Laplace of x do I have? Well, I had s squared of it on the first term and 9 of it on the second term. And so now you can see that matching that we're describing here. Gosh, that s looks like a c. I'm going to rewrite that one. Is that this is s squared plus 9, and this is also s squared plus 9. That's that matching of the frequencies that we're seeing right there. So I'm going to see an s over s squared plus 9, and therefore the Laplace of x should be s over s squared plus 9 squared. And this looks like something I've never seen before. I've never seen a quadratic squared in the denominator. So this says to me, I don't know. I got to go to my table and look it up. So let's go see if we can find something that looks like this. So we have s over, and I'm thinking, by the way, just of the form that I've seen of all these, I'm anticipating something like s over s squared plus a squared is what I'm predicting to see from my table. So let's go ahead and see if we can find that. And I know that we saw something that was like that earlier, right? And so I'm seeing something like, I mean, this kind of seems like this is it right here to me, right? S over s squared plus a squared squared. Is there a different one? No. We don't have a difference up in the numerator, so it's not this one. We do have an s up in the numerator, and that doesn't, so it can't be that one. We don't have an s squared in the numerator, so it's not that. We don't have that in the numerator, so it's not that. We don't have that in the numerator, so it's not that. And those are all the candidates that have an s squared plus a squared squared. So I think it has to be this guy right here. So let's kind of take down this information from number 9. This says that t sine of at, Laplace transform of t sine of at, according to our table, is going to be, and I'm writing this down in Word right now, I'm just keeping it up right here so I can see it, is going to be 2as over s squared plus a squared squared. So it seems to me, so I'm going to click back over, so I've copied down our information from number 9, so there it is. This is the information in blue that I just pulled out of our lookup in the table right there. So it seems to me like we just have s on top, and so what is a going to have to be? looks like we need to have s being 2as, and I need to have that s squared plus 9 is equal to s squared plus a squared. So that tells me I need to have that a is going to be 3. So sorry, let me do some scrolling right now. Need to get to my new page. Last new page of the semester right here. So it seems like a is going to have to be 3 based on the way that we've got our denominator set up right here. So therefore, we're going to need s to be equal to, or is going to need to transition into 6s right here. So I kind of want to like erase that. I'm going to get rid of that statement right there. So, all right, so let me write it this way. I feel like I'm writing this in a kind of dumb way right here. So what I'm thinking to myself is let's write this now as the Laplace transform of x equals s over s squared plus 3 squared squared. What I still need to agree with all this stuff is 2 times 3 is 6. So what I think I'm going to do is write this as 1/6 times 2 times 3 times s over s squared plus a squared squared. And I want to not write a, I want to write 3. And so now you should agree that this is exactly the general structure of this. 2 times a times s over s squared plus a squared squared. It's exactly this. I had to get that 1/6 out front because of the fact that I need a 6 up in the numerator up there to agree with this general format right there. And so therefore, we should just be looking to take the inverse Laplace of the Laplace of x should be equal to 1/6 the Laplace inverse of 6s over s squared plus 3 squared squared. And therefore, our final answer for our final problem of the semester should be x of t should be equal to t sine of 3t. Now, let's do our last confirmation here that we did this smartly. What we knew to expect was a periodic solution that has an amplitude that grows over time. This t is our amplitude term. This is our amplitude growing over time here. So let's go ahead and pop over to Desmos for our last graph of the semester here. So I'm going to go ahead and I'm going to graph our let's see here, y equals x sine of 3x. And what you can see is that this is going to grow in amplitude over time until the system breaks, right? You should notice that this is just following the lines of y equals x and y equals negative x right there are the two lines that it is following. Let me just change that also to blue and change this guy to orange. And so this is exactly what we expected to see right there. There is us starting at time 0, and we are seeing our amplitude grow over time right here. So I'm going to go ahead and take a screenshot of this guy, throw this into our notes here, and I think that's about our last topic here, guys. All right. So back over here in Microsoft Word, I think I can just conclude that we did end up seeing an equation that was exactly what we thought we were going to end up seeing, which is a trig function with a linearly growing amplitude. And boom, there it is. So this is our Laplace transforms here. Today we hit our Laplace transforms of second derivatives. Very importantly, you should recognize that looking up the Laplace transform formats that you don't recognize is absolutely a standard thing. I don't know a single person that just knows all their Laplace transforms. When I see my general structures, I can at least look at stuff like s over s squared plus 9 quantity squared and say, I know that that's one of the things that's in my table. I at least know that much right there, and that's about how much I know. Learning to use that table is a skill in itself. So that's just something that you need to be able to be practicing with on your own as well. So this wraps up our final topic of the semester. We now have a completely different way to solve differential equations in this last week by using this kind of honestly very strange idea of the Laplace transform. But it puts the challenge of the integration into something that you only ever have to do it once and save your results in a table that you can use later. And then the real challenge of doing any of these problems often ends up just being doing your partial fraction decomposition over there, which on the one hand is obnoxious. On the other hand, it's just algebra, and algebra should never be anything that's meaningfully challenging to you anymore. So this is very, very good for us that we can use these Laplace transforms to make this kind of stuff happen. So Oh, I see why that was so dang steep out there. Oh my gosh, I can't believe I'm making my last typo of the semester right there. 1/6 t sine of 3t right there. I was like, this graph seems way steeper than I remember it being. I'm going to go ahead and fix this graph, but I'll do that after I end the video now. Uh, I have thoroughly enjoyed this semester of differential equations again, even though we're online and I'm making videos. I strongly, strongly encourage you guys to keep on taking your math classes out there. I know that this means that all of you that are taking this class are now done with your calculus sequence. I know that a good chunk of you have already taken your linear algebra class. If you haven't, go take linear algebra. I hope your other big takeaway from this semester is that I don't care what you're going to do in the future, you are some version of a mathematician because you've made it this far. And if you're a mathematician, then you need to be able to program mathematics. And so I also would very strongly encourage all of you guys to, I mean, we've got summer is basically starting here in 2 weeks, as far as the date right now. That seems like a pretty dang good thing for you to be doing as sort of like your independent topic for the summer right here is learning some programming things. Get a little bit more into programming in Python. Go to Project Euler and Advent of Code and find the good problems. You can spend literally thousands of awesome hours there learning a ton of insanely practical skills for the rest of your academic and professional future. Please go do that. If you want help with that, email me. I hope that another lesson you guys learned this semester is that the only thing I like talking about more than differential equations is programming. So I want those emails. So do that. Uh, I had a great time with this semester, despite this not being an ideal setting for any of us. Yes, this concludes our lecture topics this semester. Have a good one, everybody.